Hi, I'm Tom Sturgatis, and I made an interesting visualizer for the dela contest. Um, it's only useful for the minimum grids. So here I have the best minimum grid for the 27 by 27 part, and you can see I have an array of 27 by 27 numbers here. And having the actual numbers in each space is kind of noisy. It's, I think, a lot more useful to show the largest prime factor there instead. If you mouse over, you'll see the actual number in the tooltip. And you can see that there are different darknesses. The darker numbers have a higher average greatest common denominator, and those, you can see those tend to be more in the center. Let's see. Yeah, and you can also notice that the like all the 13s are clustered together. Instead of numbers in some of these spaces, I have a symbol. So percent sign represents a 131. This one represents a 137, because so those both happen to divide into 27 squared 5 times. So in the grid there will be 5 multiples of 131 and 5 multiples of 137. So the factor of whether it's 131 or 137, those are pretty much interchangeable without affecting the score much at all. And those tend to behave, like appear in the same parts of the grid, even though they're different prime numbers. They'll tend to cluster together. And then so the significance of the percent symbol is, if you look on your keyboard, the percent symbol is above the number 5, so percent corresponds to 5. This pound sign is 3, and so on. Okay, and then the arrows, they point from each number to the ideal spot on the grid where they would like to be to minimize the total score. So like here in the middle, 700 is pointing slightly up, so it's pretty much in its ideal position. You can see the numbers on the outskirts all tend to be pointing much closer to the middle, and they would love to be closer to the middle, but it's better to have the heavier numbers closer to the center instead. Alright, and then these green numbers, those are all the prime numbers, all the ideal spots for the prime numbers. And the large green numbers, like this green 13, it's showing the average position of all the multiples of 13 on the grid. There's definitely a pattern where the distance to the center of the grid, I guess the real center is I think this guy, this 7 right here, but you can see sort of all the arrows are pointing closer to around here. You'll notice that the distance of each green number to the center is sort of related to what that number is. So like 2 is the closest to here, then 3, then 5, then 7, then 11, then 13, let's see, 17, 19, 23, 29, 31. They sort of go out further. So that's very interesting. And you also notice that Right, so the first four primes are very close to the center. Then the next the primes from 11 to let's see, all the way to 31 have exclusive access to this swath of the grid, and then yeah, then all the other primes are sort of further out here, and then you also notice that all the symbols, all these asterisks, or sorry, ampersands, no, all these @ signs are clustered together. All the dollar signs are together. All the pound signs are together, and so on. Yeah, I think you'll also notice that these so these percent signs correspond to 5, and those are sort of close to so from the center through the 5 is sort of shows this direction, and the percent signs sort of are floating that way. These pound signs, which are 3s, are sort of close to 3. These dollar signs, 4, are sort of near the 2. So these are the 2s, the 7s, so those are higher, sort of closer to the 7 than the other numbers. They're still not completely near the 7 because they these prime numbers, like 101, it still has 505, and so there's a factor of 5 in this in that group of numbers, and a factor of 6 and a 2 and a 3, 7. But it's still overall, these guys sort of tend to be closer to the 7 than the other numbers, than the other primes. Then got a factor of 8 there. Then 6, you might expect 6 to be a little bit closer, a little more to the right, but it still has a factor of 5, pulling it this way. Yeah. So here's the 26 by 26 grid, and you'll see a similar pattern where 2 is close to the center, then 3, 5, 7. Then all the next primes are in a swath, and the other guys are clustered together by symbol. It's a little bit weird that this @ sign is by itself, but yeah, so 25 by 25, 24, 23, 22, 21, 20, 19, 18, 17, 16, 15, 14, 13, 12, 11, 10. Even in 10, you can kind of has the same patterns too. And then, yeah, if you're curious, this is what the max one looks like. So all the arrows are pointing pretty much to the center, so it's just a big mess. So one way to find the total score of the Delacorte grid is to find the centers, not of just the prime numbers, but of all the factors. And then for each number, you can find, like let's say for the number 11, you can assign a score for each position on the grid. So very close to 11, it'll be near 0, and far away from 11, it'll sort of be the distance squared times 11. So you can sort of come up with a static scoring scheme for each single number. So, and not just the prime numbers, but like for 44, it would be influenced by where the 11 is, where where 22 is centered, and so on. But anyways, so for each number, you can come up with a score for that number being in every position. And it turns out that if you want to place all the numbers, maybe you just place them randomly. You can run a order of n to the 6th algorithm to either tell you that that placement is optimal for the total score, or it can tell you a chain of some entries to cycle to reduce the score. So if you keep on running this algorithm over and over, then eventually you'll get you'll reach the minimum. And yeah, it's just a tricky application of the Floyd-Warshall algorithm. And yeah, so if you feed it this grid, with these centers for all the factors, then you'll it'll just tell you that it's already optimized. But you could take the centers and start with a random grid, and it'll eventually it'll keep on finding things to optimize, and eventually it'll end up with this same grid, even though it starts with a random grid. And so that's kind of neat. Maybe you can specify the positions of all the centers of the factors, and come up with a good grid that way. But that's a lot of work to come up with all the centers. But maybe if you just position all the prime, maybe there's a way if you just position all the prime all the prime number centers, that would be enough. And it turns out that so 5 is centered here, 7 is centered here, then 5 times 7, 35. It'll be centered somewhere between these two guys, so you can sort of linearly interpolate and then sort of weight it closer towards the 7, I think, and come up with a scheme. I tried to do that, and it kind of worked, and you could do some neat things. So I could swap the 7 and the 5, or I don't know, let's say swap the positions of 19 and 31, and then re-optimize the grid. So now I have pretty much my same result, but with the all the with the factors of 19 tending to be close to here and 31 being close to here, and I could run my usual simulated annealing and see if maybe I get a better result. It turns out I don't think that was very useful, but I was hoping that I could use that technique to come up with a good starting points to optimize